Assalamualaikum warahmatullahi wabarakatuh. My name is Falihah alias Salsabila, and if you clicked on this video, that means you are also an AIS student who might be on the brink of death due to physics. Don't worry, I am too. I am too on the same boat as you. But fortunately, I am here to make an explanation on some concepts on electricity. Today, in this video, we are going to talk about three main concepts, it being current and charge. The next one is potential differences, not just potential, but potential differences and power. And then the next and final one is resistance and resistivity. So, these are our subject learning subject learning objectives. Yeah, I think that's the long version of SLO. But yeah, we're going to talk about how a circuit actually works. Now, if you take a look in a circuit, there must be something called a cell, and this cell is connected within closed wires to a component. Now, this component can be anything, but my example here is a light bulb. The question is, how does a light bulb being in a circuit, how does the circuit lights up the light bulb, So how does it make it light up? Now, the answer to that lies within the battery. So we're going to take a closer look on that. So a battery has something known as chemical potential energy. Now, if it is plugged into the circuit within a closed circuit, this energy will be transferred to charge carriers. So charge carriers, now having energy, they will move within the wires and they will travel and eventually they will reach electronic components. Now, the energy that they bring will be transferred to these electric components, making them work. Like for instance, this one, it lights up the light bulbs and afterwards the charges will come back and repeat the whole cycle. So basically, that is the simple way to explain how a circuit works. Now, let us go to our first topic, which is 9.1, talking about current and charge. What is a current? So, the definition of current is simple. It is the rate of charge. We can write this down in an equation as I will be equal to charge, or write it down as Q per time, because we know that rate is anything divided by its time. Alright, let's label it. Q will be the total charge, remember, total charge, and then T is the time taken or the time intervals, and finally I is the current. Alright, that's clear enough. Let's take down the units. Current being, that's the wrong color, let's change it. Current being amperes being A, and then time being seconds, and total charge being coulombs. Now, from this equation alone, we can define what charge is. You could go ahead and write it down. Q, write it down as, Q is equal to the charge, the current times its time. Now, this is our equation. Alright, I feel like I should box it, so it's clear. Cool. So, now, one thing to take note of is charge, they are quantized. I don't know how to pronounce it. Correct me if I'm wrong, I'm going to correct it when I'm editing. But that just means that a single charge carrier, I'm going to write that down. So a single charge carrier, not carries, will equal to its magnitude, or its quantity is equal to 1.6 multiply to 10. Oh, no, wait, why did I write 19? It's 10. Hang on, let me erase that. 10 to the power of minus 19. So yes, this is our Q, or it's known as electron number, if I'm not mistaken. I'll correct that in editing as well. Okay, now charge carriers. So to find a charge, which is the total charge, we could just multiply the number of charge carriers to its Q, or its quantized values, which is that. Simple as that. Now, using this equation, we can actually find something known as the drift velocity. Yeah? Drift velocity is how fast the electrons are moving within the wire. So let's write that down, shall we? Blue. Okay, drift velocity. Oh, that's so bad. Dear God. Let's erase that. Oh, wrong button. Sorry. Let's try that again. Drift. Oh. Velocity is to calculate this, you'll just need the regular equation of velocity that we learned in kinematics, which is the displacement divided by its time. Now, the question is, how do you get this value? Well, we have to derive the equation I is equals to Q per T. Let's write that down, shall we? I is equals to charge per time. Now, we know that the charge is number of charge carriers times its quantized version, so let's write that down and divide it by its time. Okay. Just like so. Now, how do we find this n? An easy way. So sometimes the number of charge carriers are too big, so scientists, they simplify it by turning it into number of density, which is basically the number of charge carriers per volume. So let's write that down. Number of density, or n, is equal to number of charge carriers per volume. Did I say velocity before? Oh, my bad. But it's volume, okay? So we could plug that in our equation directly. We could substitute the big N, the capital N, with this new equation. Okay? So, number of density times its volume times its quantized number per time is equal to I. Alright. Now, where do we get this volume? Well, we could see that the wire is a cylinder, which has area, so the volume is area times length. So yeah, we could also plug it in the equation. Substitute V with A and L. So number of density times area times length times quantized number divided by time. And finally, our last derivation, since we know that velocity is s per time, or the displacement, let's take a look at the wire. Oh, so actually the electrons travel along the length of the wire. So the s here is actually the length. So yeah, we could plug that in. So actually, length per time is equal to velocity. So I, or current, is equal to number of density times its area times its drift velocity times its Q. So that is the equation, ladies and gentlemen. After a long derivation process, we finally got it. And we can find drift velocity with this equation. Alright, cool. Nice. Alright, now we are going to 9.2, where we are going to talk about potential differences and EMF. When we are talking about these two components in electricity chapter, we are actually talking about electricity, so let's go directly. What is potential difference? Potential difference is the energy transfer per unit of charge from one, that's not how you spell charge. Charge from one point to the other. And EMF, its definition is the energy transferred per unit of charge in a whole circuit. Alright, so let us underline the main keywords from these two definitions. The first one is energy transfer, and then the next one is per unit of charge. This is the same here, energy transfer per unit of charge. So what can we deduct from these two equations? Well, we could write it as two definitions. We could write it as one equation. So we're going to write potential differences and EMF as V will be equal to energy transfer, or W, work per charge. So this is our definitions. This is voltage, or PD, EMF. This is energy, and this is charge. Now, the units, this is volts, this is coulombs, and this is joules. So yes, this is the equation that we need to know. Now, EMF is the total energy here. Oh dear, I hope that's okay. Now, if you enter, 12 volts, not G, my mistake. And PD will be the one here. So this is known as EMF, because it's a whole battery, and this will be known as PD, because it's only from one point, it's the voltage in the resistor only. Alright, now we can move on to electrical power. Electrical power is, let us write this down. Electrical power is the rate of energy transfer. Now, the equations are, let's talk about the first one, the main one. The first equation is simply power is equal to current times voltage, which we are going to go back in a bit. But for now, we're going to continue and talk about resistance. What is resistance? Alright, resistance is defined as the voltage divided by, let's use a fancier term. Let's say it as the ratio of PD to its current. Now, we could write this equation as R is equal to, or resistance is equal to, V, or PD, per I, or current. Now, this is actually known as the Ohm's law. What is an Ohm's law? So an Ohm's law is where hang on, let me try to check it out. Alright, I'm back. So I checked, and actually the definition for Ohm's law is when in a component the current is proportional to its potential difference. Now this equation, you can write it down as this. V will be equals to IR, which proves this statement over here. Now we're going to look at a few graphs with the PD as the x-axis and the current as the y-axis. This one, the first one, we could see that it is a straight line indicating that this follows, that the current is proportional to its voltage. So we could say that this is ohmic, or it follows, let's use a different color, it follows Ohm's law. But what about these other three? We could see that the gradient is not straight, That means number 2, number 3, and number 4, they are considered as non-ohmic, which means they disobey. Oh, wrong color. They disobey Ohm's law. Now, let's check out these three different components of non-ohmic components of circuits. The first one is a diode. We could see that it is, you know what, actually, look at the difference yourselves and analyze how it differs from each other, because now I'm going to move on to the next and final topic, which is actually the factors affecting resistance. Now, it is a fact that when more collisions happen between the charge of carriers and its ions, they will have greater resistance. Greater resistance. So this means when the temperature increases, the resistance will also increase. Why? Because there will be more collisions, since the temperature increase will cause a higher kinetic energy. Now, for the other factors, so one of the factors, okay, let's write this down then. So factors, the first one is temperature. Now, what are temperature? Now, what are the other factors? We could see through this equation. Now, we could see that this is resistance. Resistance is equal to, what is the symbol? Well, this symbolizes for resistivity, multiplied by its length, or length of wire, multiplied by its area, or area of wire. So I could actually draw a graph to make it easier for you to understand, but I want to highlight on how to use this equation to figure out which factors does what to the resistance. Okay, let's just draw it out, shall we? We first have temperature. Okay, that's done. Let's look at the other one. Let's look at resistivity. Now, when the resistivity increases, what will happen to the resistance? Well, we could see, since they are aligned like this, just look at the pattern. I don't know how to explain that bit, but if the resistivity increase, the resistance also increase. Now let's look at length. length of wire increases. Why did length of wire increases? That means the resistance also increases. Now let's look at area. Area and resistance. Oh, but this time area is not. It's below the. How do I explain this? It's like not aligned. This is a different. I can't explain it well. But look, this is above and this is below. That means if it increases, the area increases, the resistance will decrease, because this means if it's below like this, it means we can write it down like this, R, I think, which means it's like proportional. That's not how you write proportional. Correct me if I'm wrong, but like this is out of pure memory. I should have done research on this, but this is like R is inversely proportional to area. So yeah, these are the factors affecting the resistance. So this is area, and this, hang on, let's rewrite that. Sorry. This one is length, and this one is area. And now we're going to write this as proportional to R, and this one is inversely proportional to R. Voila, that's all. Alright, I hope it is understood. These are all the topics that I'm going to talk about today. So yeah, that was fun. I'll see you in a bit where I'll explain other concepts. Bye loves, good luck on AIS. I'm wishing for the best.